All right, today we are going to tackle one of the most absolutely mind-bending mismatches in all of physics. It's a puzzle so huge, it really makes you question our whole understanding of space-time. But we're also going to look at a surprisingly elegant solution that, well, it might just unify everything. Let's dive in.
So I want you to imagine this for a second. You're an engineer building a massive bridge, and your calculations are off. Not by a little bit, not by a few feet, but by a number so ridiculously large you can barely even write it down. That's the kind of problem we're talking about here. And just to be clear, this is not a hypothetical. That number, a 1 with 67 zeros after it, that represents a real disagreement between a major theoretical prediction and what we actually see in reality. It's a genuine cosmic crisis, and it desperately needs an explanation. Okay, so let's set the stage for our little cosmic detective story. The mystery really begins when we try to connect the physics of the incredibly, impossibly small with the world that we all, live in and observe. Here it is. This is the absolute heart of the problem. You've got these theories of a granular, kind of pixelated spacetime, right? Well, they predict that there should be this enormous energy tension in the vacuum of space. The number they come up with is a staggering 10 to the 67. But when we actually go and measure it, we get about 0.2. The gap between those two numbers it's just astronomical. I mean, let's be real. This isn't something you can just ignore or brush off as a rounding error. A screw-up this big means our understanding is fundamentally broken somewhere. It's a huge problem for an entire class of theories trying to explain the ultimate nature of reality. But what if we've been looking at this whole problem the wrong way? Let's introduce the hero of our story, this really powerful idea called the renormalization group, which kind of acts like a zoom lens for the laws of physics. At its core, renormalization group flow, or RG flow for short, is a beautifully simple concept. Think of it as the physics of zooming. It basically tells us that the rules of the game can actually change depending on your perspective, whether you're looking at something as small as an atom or as big as a galaxy. Now, this is where it gets really interesting, because this represents a huge shift in thinking. We're all taught to think of physical constants, like the strength of a force, as being, constant. But RG flow comes along and just throws that whole idea right out the window. And this illustrates that change perfectly. The old assumption, a property is just a fixed number, that's it. The new idea, powered by RG flow, is that these properties actually run or evolve as you change the scale you're looking at. So a force might be super weak up close, but get really strong from far away, or maybe the other way around. Okay, so the big question, how does this zoom lens idea solve our insane 67 orders of magnitude crisis? Well, this is where we actually build the bridge, connecting the physics of the tiniest possible scale with the world of protons and neutrons that we're all familiar with. So here's how the calculation actually works. First, you start way down at the fundamental pixel level of reality, that's the Planck-scale, with its gigantic predicted energy. Then you apply the specific zooming rule for the strong nuclear force, and then you just let it run. You flow across a vast cosmic distance, zooming out by a factor of 10 to the 20 until you finally land at the scale of everyday matter. And the result? After that incredible journey across all those scales, the RG flow calculation spits out a value of about 0.2 GeV². This isn't just in the ballpark, it's a nearly perfect match with what we actually measure in experiments. That 67 order of magnitude gap, it just vanishes. It's gone. And I really have to hammer this point home because it's the most important part. This was not a case of physicists just tweaking the numbers and plugging things in until they got the right answer. No way. The starting value was set by the physics of the Planck scale. The zooming rule was derived from the theory. The final number is a genuine first principles prediction. It's absolutely astonishing. But wait, because the story actually gets even better. This solution doesn't just fix one glaring problem. It hints at something much, much deeper, a kind of fundamental unity among all the forces that run our universe. So it turns out this whole idea of properties running with scale applies to all four of the fundamental forces. But, and this is the critical part, each one follows its own different path. Each force has its own unique RG flow. This table lays it out so well. As we zoom out from that super tiny Planck scale to our everyday world, you can see the strong force actually gets stronger, and that's what traps quarks inside protons. Electromagnetism pretty much stays the same. The weak force gets stronger so fast that its range becomes tiny. And then gravity, kind of counterintuitively, actually gets weaker. And this leads to a really profound implication. Even though all four forces take these completely different journeys, if you trace them all back to the starting line, all the way back to the Planck scale, it really looks like they all start from the exact same point, with the same initial strength. What's so amazing is how this unification happens. It doesn't need any of the exotic, super complex theoretical stuff that physicists have been proposing for decades, things like supersymmetry or extra dimensions. It seems like the granular structure of the vacuum itself just does the job, naturally.
Of course, a beautiful idea is great and all, but this is science. You have to be able to test it. A theory isn't really a theory unless it makes predictions that we can actually go out and look for in the real world.
And this theory makes two very clear, very testable predictions. First, it says that the strength of the strong force shouldn't be perfectly constant. It should change just a tiny, tiny bit as you probe it at smaller and smaller distances. And second, it predicts that gravity itself should get a little bit stronger than Newton's law says it should be, but only when you measure it at scales below a millimeter.
So where are we at right now? Well, the effects the theory predicts are incredibly subtle. They're just beyond the reach of our most sensitive experiments today. But physicists know exactly what they're looking for. The targets are set, and the experimental hunt is officially on. So, what's the big takeaway from all this? It's that one simple, powerful idea. The idea that physical properties flow and change with the scale of observation could have the potential to solve a 67 order of magnitude problem and naturally unify the fundamental forces of nature. And it all leaves us with this one last fascinating thought to chew on. Maybe the universe, at its most basic level, isn't some smooth, continuous thing. Maybe, just maybe, the solution to some of the deepest mysteries in physics is that the fabric of reality itself is made of tiny, discrete, granular bits.